Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIWA campus. Here we will cover Fourier transform and some of their properties as well. Let's start the lectures. And as we discussed earlier in previous classes, that there can be a two type of signals. One can be a continuous and the other can be a discrete. Further, in continuous, there can be two types, like one can be a periodic signal and other can be a non-periodic signal. And to analyze the periodic signal, we use the Fourier series, which we already covered, right? Because this is an analysis tool to convert any signal in terms of complex exponentials, usually e j omega naught t, right? So we studied in detail in the previous chapter that periodic signal to convert into the complex exponential, we use the Fourier series. From now on, we will focus on non-periodic signal, which is for that the analysis tool is the Fourier transform. So this will be the main topic of this video as well. And similarly, for the discrete case or the digital case, there are two types. One is periodic and other is non-periodic. For periodic, we already covered in the previous chapter the discrete Fourier series. Whereas for non-periodic, we will discuss later on about discrete time Fourier transform, DTFT, and Z transform. Right? These are all the categories which we have to cover later on as well. So from now in this chapter we will cover the Fourier transform, which the Fourier transform is used to evaluate the non-periodic signals. Introduction. Let's introduce why we need a Fourier transform and what is the difference between Fourier transform and the Fourier series, and where can we adopt Fourier transform and where can we use the Fourier series. So we studied that the representation of a periodic signals as a linear combination of complex exponential. We already studied that the periodic signal can be expressed any type of periodic signal. It's not necessary a sine or cosine, but for example square wave and any other type of periodic signal, we can write that periodic signal as a linear combination of complex exponential. Linear combination of complex exponential means that we use we combine various different frequency complex exponentials and linearly and then create a periodic signal. Here in this chapter we will extend the concept to apply to signals that are not periodic. So previously we were dealing with a periodic, now we are extending the concept. If the signal is non-periodic, then how can we evaluate uh, them those type of signals? For periodic signal, the complex exponential building blocks are harmonically related. Harmonically related means that, for example, omega naught is the your baseline frequency or the fundamental frequency. Then next frequency will be 2 omega naught, 3 omega naught, 4 omega naught. These are harmonically related, right? For aperiodic signal, they are, so for aperiodic signals, they are infinitesimally close in frequency, like they are very much closer to each other, very small gap between them, and the representation in terms of linear combination takes the form of an integral rather than sum. Previously, you have seen that whenever we are dealing with harmonically related frequencies in Fourier series, we have a summation sign over there because we are adding them uh, and the difference between them are substantial. Whereas as there is very much close to each other in frequency, so instead of summation, we will take integral here as a sum. To sum them, like harmonically related terms, linear combination of terms, we will take the integral rather than a summation in Fourier transform. The resulting spectrum of a coefficients in this representation is called Fourier transform. So after linearly combining them, then the resultant spectral coefficients. So what are the spectral coefficients? Previously, you know that there was a coefficients AK. Similarly, here the term AK is type of a spectral coefficient. Uh, However, we will represent it with some different notation, but its meaning is more or less the same, right? After taking Fourier transform, the signal can be viewed as a periodic signal with an infinite period. You know that as we highlighted that for a periodic signal, we are focusing on using the Fourier series. Whereas for a non-periodic signal, we are focusing on Fourier transform. However, if you say that, for example, this is a signal, it has a period which is going long and long, right? And if we say that its period is till infinity, right? Its period is equal to infinity, time period is infinity. What does it mean? It means that after infinite period, the signal will start repeating again. For example, this will start repeating from here again after infinite period. So it means that this signal is a periodic signal, but the period is too long. It means period is, for example, too long, long till infinity. So it will definitely repeat, but infinite amount after infinite amount of time. So in this sense, we can view this non-periodic signal as a periodic signal, right? So the other important point is that it converts time domain signal into a frequency domain signal. So by using Fourier transform, we usually convert the time domain signal. Time domain means if you have an x-axis time and here you have an amplitude, right? So after taking the signals Fourier transform, right? For example, this is your signal and you take Fourier transform. So the signal here at x-axis there will be f instead of t. So this will be your some kind of a Fourier transform, right? Fourier series versus Fourier transform. As I already discussed, but let's discuss again. Fourier series is a discrete representation of a periodic signal as a linear combination of complex exponentials, right? The continuous time Fourier series can't represent an aperiodic signal for all time. So the Fourier series, by using Fourier series, we cannot represent a periodic signal. Aperiodic and non-periodic meaning is same. Aperiodic we sometimes call aperiodic or was sometimes named as non-periodic signal. So the Fourier transform, Fourier series cannot represent an aperiodic signal for all time. So Fourier transform, a continuous representation of a not periodic signal or a aperiodic signal as a linear combination of complex exponentials. So what is Fourier transform? We have a representation of a non-periodic signal as a linear combination of complex exponentials. The continuous time Fourier transform represent an aperiodic signal for all time. So continuous time Fourier series doesn't represent aperiodic signal for all time, whereas continuous time Fourier transform represent aperiodic signal for all time. So a not periodic or aperiodic signal can be viewed as a periodic signal with an infinite period. As I already mentioned, that if you have a non-periodic signal, however, we can still name it as a periodic signal, but the period will be infinite. Okay, development of a Fourier transform. Development means that let's derive the Fourier transform general equation here, right? So let us first consider the following periodic signal. For example, we have a periodic signal x of t, whose amplitude is 1 for t less or equal to t1, right? Whereas for t greater or equal to t1 it's 0, less than t by 2 it's 0. So where xt is equal to xt plus t, it means that it's periodic. The Fourier series coefficient of xt are, the Fourier series of this coefficient are, previously in some example we already solved this signal because this is a square wave type of signal we already solved. So here they are just referring, we are just referring that you can solve yourself again if you want to solve this. So xt is your periodic signal and you want to find the Fourier series. So ak is the Fourier coefficient. So by doing using that equation which we already solved in the previous videos, you can obtain the Fourier series coefficients a of k equals to 2 sine k omega naught t1 over k omega naught t. So if we substitute k omega naught is equal to omega, then this equation becomes 2 sine omega t1 over omega t, where at omega is equal to k omega naught. So the spectral coefficients, so the coefficients, Fourier series coefficients become 2 sine omega t1 over omega t. Now multiply both sides by t. capital T on both sides yields you Tak equals to T 2 sine omega T1 over T omega, because by multiplying by T here the T will be cancelled out, which is the normalized Fourier series coefficient. Now this you can name it as the normalized Fourier series coefficient. Pictorially 4.1 indicates that the normalized Fourier series coefficients Tak are bounded by the envelope, this one, 2 sine omega T1 over omega. So for example, this was our x of t, which we written previously by equation. Now pictorially we can see here it has a value from 0 to t1, and then it repeats again after period time t, then repeats again after period 2t, right? And whenever we take the Fourier series, then the Fourier series coefficients ak, this one ak, uh, is equal to a naught a1 a2 minus a1 a minus a2, this one, right? So Fourier coefficients of xt for some time interval t. Here the time interval is we didn't mention, just a general time interval. So you can see that this x omega is the envelope. This dotted line is the envelope, right? So if this is x omega, is the envelope of a signal. Okay, so previously we take that the effect of the varying t on the Fourier transform. So when t increases, right, the spacing between consecutive AK reduces. Look at the spacing, A0, A1, A2, they are now getting closer and closer. However, the shape of the envelope function, this is envelope function, x omega 2 sine omega t1 over omega t, this is envelope, the dotted line which I already mentioned, remains the same. There is no change on the shape of the envelope. This can be seen from figure. For example, previously there was a repetition from here, this point. Now they are repeating at t dash, right, which is greater than t. So whenever we take the Fourier series coefficient, because this is a periodic signal, for periodic signal we take the Fourier series. So the Fourier series, after taking Fourier series, you are noticing that they are getting closer and closer. So in the limiting case, where t approaches to infinity, it means that when as we are increasing t, continuously increasing t, for example, t is equal to 20, 30, 40, 50, up to we reach the stage where t becomes infinity, too long. Then the Fourier series coefficient Tak approaches the envelope function. So what does it mean? Previously there was a step is very much small, envelope has bit small steps, but whenever this t approaches infinity, it the envelope becomes continuous, right? There will be no step for this, right? So this suggests that if we have an aperiodic signal, we can treat it as a periodic signal with t is approaches to infinity. You know that for a aperiodic signal we are doing the Fourier transform, but they are mentioning here that if we have an aperiodic signal and we can treat them as a periodic signal with t is approaches to infinity. So whenever t approaches infinity, we can treat the conventional aperiodic signal as a periodic signal and can apply the Fourier series as well. Then the corresponding Fourier series coefficient approach to envelope function. So the corresponding Fourier series approaches the envelope function. The envelope function is called the Fourier transform of the signal xt. This envelope function x omega is called the Fourier transform. So this is x omega, which is Fourier transform of a signal. Now let us study for Fourier transform in more formally. Derivation of a Fourier transform. Step 1. We assume that an aperiodic signal xt has a finite duration. That is, xt is equal to 0 for t greater than t by 2 for some t. Since xt is a aperiodic, uh, we first construct a periodic signal x tilde t. So, as I already mentioned that xt is a aperiodic signal. So, to convert them into periodic signal, we will first uh, construct a periodic signal, right? So, we mentioned here that x tilde t is equal to xt for minus t greater than minus 2 by t by 2 and less than t by 2. And if it is periodic, it means that x tilde t plus t is equal to x tilde t. So pictorially we have this is x of t, which was an aperiodic signal, and we convert into periodic signal in this way. Look at this. This is x tilde t. So the signal is repeating here, here, and here, right? Step 2. Since xt is a periodic signal, any signal which is periodic, we can represent them in terms of a Fourier series. So we may express x tilde t using the Fourier series and different complex exponentials. For example, x tilde t is equivalent to k equals to minus infinity to infinity ak e j k omega naught t. We already derived in previous chapters this one. So where ak, you know that ak is equal to 1 over t, t period is t, so x tilde t e minus j k omega naught t dt. The Fourier series coefficients can be further calculated. Now we have to calculate the Fourier series coefficients, and as we know that there is a value of 1 only within the amplitude within the duration minus t by 2 to t by 2. So replace this with a period minus t by 2 to t by 2 x tilde t e minus j k omega naught dt equals to 1 over t minus t by 2 t by 2, and as you know that x tilde t is equal to x of t, right? Because this x tilde t is equal to x of t for the mentioned period, this time duration. So we can just replace x tilde t with x of t, and as we already discussed that xt is equal to 0 for t greater than t by 2. So for example, uh, look at this. This is our period t by 2, right? And then we have a minus t by 2 here, right? For this we have a value or amplitude equals to 1, for example, whereas for uh, next time period t till this portion we have a amplitude 0. There is nothing here. So xt is equal to 0 for t greater than t by 2, it is 0. So we can say that as you are focusing on the infinite period as well, so we can just replace minus infinity to infinity, minus t by 2 with minus infinity and t by 2 by infinity. We can change the limit as well, because as I mentioned that it can be treated as a periodic signal when we extend the limit from limit to the infinity, t approaches to infinity. So we can write in this way. So if we define x j omega naught, this is a Fourier transform, equals to minus infinity to infinity x of t e minus j omega t dt. You must remember this. We will utilize this equation further on as well. Then it holds that ak equals to 1 over t x j k omega naught t, right? Consequently, substituting 4.5 4 into 4.2 previous equation, we yield this one x tilde t equals to k equals to minus infinity to infinity 1 over t. We are now putting this value in the previous equation, summation 1 over t x j omega j k omega naught e j k omega naught t equals to minus infinity to infinity 1 over 2 pi, right? X j k omega naught, right, and e j k omega naught omega. In the next step 3, we now note that x tilde t is the periodic padded version of xt. So it is a periodic version of x of t. When period approaches to infinity, the periodic signal approaches x of t. So whenever the x tilde t approaches x of t, when the period is infinity, right, in this way, as t approaches to infinity. Moreover, when t approaches infinity, equivalently omega naught approaches to 0. So when t approaches infinity, you must remember omega naught approaches to 0. The limit of the sum in equation 4.5 becomes an integral. As we already mentioned previously, when t is approaching to infinity, so limit of summation will be converted to the integral. So this summation will be converted into integral, right? So we can rewrite as minus infinity to infinity 1 over 2 pi x j omega e j omega t d omega. Graphically, this can be seen in the figure below. For example, this is your k omega naught, right, and this portion, and this is your next frequency k plus 1 omega naught, and this is your previous frequency k minus 1 omega naught, and this is your envelope, which is xj omega e j omega naught x j k omega naught e j k omega naught x j k plus 1 omega naught e j k plus 1 omega naught t. So we can represent the signal pictorially in this way, the Fourier transform of a signal. So combining the previous equation, we finally have xt equals to 1 over 2 pi, because 1 over 2 pi is a constant, but bring it out, minus infinity to infinity x j omega e j omega naught e j omega t d omega. These the two equations are known as the Fourier transform pairs. Uh, 4.3 is called the analysis equation. We already discussed, because we are analyzing the time signal in the Fourier domain. And 4.8, this one is called the synthesis equation. These are same like previously in Fourier series we have an analysis equation and synthesis equation. Here this is a synthesis equation, and the previous 4.3 is an analysis equation, because we are gathering Fourier domain information and reconstruct the time domain signal. To summarize, we have the Fourier transform xt omega naught of xt. If you have a xt given signal, you want to calculate the Fourier transform, then just take the integral and from minus infinity to infinity and integrate. Then you will get the Fourier transform. And the inverse of a Fourier transform, when you have a time domain signal, you will get the frequency response, right? And whenever you have a frequency domain signal, for example xt omega, then you want to take the inverse Fourier transform, which is given to, which is equivalent to x of t 1 over 2 pi minus infinity to infinity x j omega e j omega t d omega. Here you have a positive sign, whereas here you have a negative sign. Right? Let's discuss the convergence of Fourier transform. For convergence, as we already discussed in the Fourier series, there are three properties. If the signal satisfied that three properties, then it is possible to take their Fourier transform. Otherwise, it is not possible to take the Fourier transform or the Fourier series of that signal. So there are three conditions named as Dirichlet equations, are the sufficient conditions for the convergence of Fourier transform. So for the convergence of Fourier transform are similar to the condition of the continuous time Fourier series. The first one is that xt must be absolutely integrable. What does it mean? That it means when you integrate x of t and amplitude for minus infinity to infinity, the result should be less than infinity. If it is not less than infinity, it means that it is not absolutely integrable over the complete range. Then if it is not absolutely integrable, then the Fourier transform of that signal is not possible. Second condition B is that xt must have a finite number of maxima and minima within any finite interval. For example, you take t time interval 1 to 5. So there should be maximum finite number of, there should be finite number of maximum points or minimum points within that interval. If it is infinite, then continuous time Fourier transform is not possible. The last condition is that st must have a finite number of discontinuities of all of finite size within any finite interval. So there should be a continuous finite number of discontinuities within any finite interval. Let's see these conditions. The first one, absolutely integrable, the A. If it is absolutely integrable, it is not going to infinity within any time period, then it is absolutely integrable. The second is that there should be a countable number of maximum and minimum points in an interval, for example. Third one is that there should be a finite number of maximum and minimum as discussed. So these three conditions A, B, C must be satisfied before we can evaluate further for a Fourier transform. If one of these conditions is not satisfied, it means that we can't evaluate the Fourier transform of that signal. Let's take some examples about the Fourier transform. Consider a rectangular pulse signal, this x of t, which is minus t1 to t1, the value is 1. For example, mathematically we can write it as x of t is equal to 1 for t plus absolute less than 1 and 0 for t greater than t1, as we can see from this picture. As shown in figure 4.8a, this one, applying equation 4.9, which we already derived to take the Fourier transform, we can find the Fourier transform of this signal as this one. X j omega and the limit is minus t1 to t1 because there is nothing outside that limit. There is no value outside this limit, it is 0. So we change the limits from minus infinity to minus t1 to t1, and as the amplitude is 1, so 1 into e minus j omega t dt. When we take the integral, so by putting these values, the outcome will be a this sinc function. This is called a sinc function. You can derive it further as well for your satisfaction. However, we already derived that previously. So it is equivalent to 2 sine omega t1 over omega. So this will be the Fourier transform of a rectangular pulse signal. So whenever we plot this, this is your original signal and this is the Fourier transform x j omega, right? X j omega. So you can see that this function, which is has a maximum value at 0, and then at each crossing it intercepts the 0, right? And goes on. So it's like this function is known as a sinc function, SINC, sinc, right? And it can be written in terms of sine shape in this way, sine omega t1 over omega, right? And this crossing is are the pi by t1 and the minus pi by t1. And from here you can notice that this function will continue for omega in this way. This will goes on in this both directions, right? In this way. The reason is that for any sharp transition, if you from notice from here, this is time domain signal because on the x-axis here you have a time. You can notice that from at continuous at the time axis, suddenly there is a sharp transition. For example, there the value was 1 and then suddenly it becomes 0. So you know that when time is equal, frequency is the inverse of the time, right? 1 over t. So if the time is suddenly becomes 0, then what will happen? There will be infinite number of frequency components. So that's why this signal will continue for infinite number of frequencies. This will not decay soon. So here we also have a plot one to the same plot just to show you the peaks of the Fourier transform magnitude drop slowly. This is because the pulse function has a sharp transition which contributes to very high frequency in the signal. Has a sharp transition, so there will be more number of frequencies. Another example, x of t is equal to e minus at ut, where the condition is that a should be greater than 0. If a is not greater than 0, the result will be different, and maybe the Fourier transform will not be valid as well. So this condition is necessary there. And so from equation which we already derived, Fourier transform is equal to x j omega 0 to infinity. We have a e minus at ut because due to the unit step function, a limit changes from 0 to infinity instead of minus infinity to infinity. So then take the Fourier transform e minus at e minus j omega t dt. So whenever you take the integral, you will get 1 minus 1 over a plus j omega into e minus a plus j omega into t 0 to infinity. When you put these values, you will finally get this one 1 over a plus j omega. As you can notice from here that the x j omega is a complex term. What is the complex value? Complex value means they have a real part and the iota or the j part as well. So we have two things here. To plot this signal, we need now magnitude and the angle as well. Since the Fourier transform is complex value, to plot it as a function of omega, because we need to plot as a function of omega. Omega means frequency. We express x j omega in terms of magnitude and phase as well. Magnitude is that x j omega double bar, this is the magnitude, so which is equivalent to a square plus b square. So 1 over a square plus b square over under root, right? And the phase is minus tangent inverse b over a. So b is omega and a is a, right? So this way we can calculate the phase. Each of these components is sketched in figure 5.5. On the next slide I will show you. But the thing you should remember, if a is complex rather than real, for example the value of a here is a complex number rather than real, then xt is absolutely integrable as long as the real of a, when we take, if it is complex for example, and then complex has a real part and as well as imaginary part, but when we take the real part it should be greater than 0. In this case, the preceding calculation yield the same form of x omega t, that is 1 over a plus j omega. So there will be no effect on the result as well. Okay, let's see. This is your given signal, right? And this is the, sorry, this is your given signal. This one, E minus something, E minus AT into UT, right? This is our given signal, and we have taken the Fourier transform, right? The Fourier transform has a magnitude and a phase. So this is your magnitude plot, right? And this is your phase plot, right? So magnitude, you can see that it's the x of j omega double bar. It means magnitude. So it has values. You can just try uh, putting different values of a here. So you can see that at a you will get this value 1 under root 2 over 2a, and minus a you will get similarly under root 2 over 2a minus, right? For phase you can plot, and you are getting this type of a phase plot, right? So uh, this is another representation of the same magnitude. From here you can notice that the Fourier transform magnitude drops much faster than for the pulse function. Previously you noticed that the Fourier transform for a pulse, because pulse has a sharp transition, this is pulse, and the Fourier transform of this one was like a sinc function. It not continue, drops suddenly. It has some endpoints as well. Whereas in this case you can see that pulse jumps there, but just a continuous drop. The reason is that the given signal has no sharp transition. That's why the frequencies are, there will be less number of high frequency terms. Okay, let's take another example. You have a signal x of t, e minus a double bar t. Double bar means that this can be a positive and negative absolute value, right? So far the condition given is that a is greater than 0. So this is your x of t, right? Now you have to take the Fourier transform. To take the Fourier transform, minus infinity to infinity, e minus a positive t, for example e minus a minus t, and e minus a plus t, right? So it means that you can divide into two portions, minus infinity to 0, so e a t, right, for a minus side, and e minus j omega t for positive side, because here the t will be positive, so e minus t at into e minus omega t, e minus j omega t here as well, right, dt. So whenever you take the Fourier transform of this side, you will get a 1 over a minus j omega integral of this side, and the other side 1 over a plus j omega. By combining, you can write 2a over a square plus omega square. In this case, x j omega is a real, and it's illustrated in figure in this way. This is the Fourier transform of this x of t. So it is in the omega domain. So the plot will look like in this way. So you can just plot by using MATLAB, or using hit and trial. You can just see it will follow this trend. Before we wrap up this lecture, let's take one more example. For example, you need to find the Fourier transform of a unit impulse signal. Unit impulse is delta t. Now you have given only unit impulse and told that to find the unit impulse function Fourier transform. It is in time, and you need in frequency, how it looks like. So using the equation x j omega minus infinity x t e minus j omega t dt, and the shifting property of the impulse we have. So you know that omega t equals to 1 only at which point? When t equals to 0, right? When t equals to 0. And for rest of the time, it has always a value of 0. So this integral has no role to play, because for 0 it is only 1. So when we put 0, it becomes 1. So e minus j omega, here we will put 0 as well instead of t. So it becomes totally 1. So what does it mean that x j omega is equal to 1? It means that unit impulse has equal contribution at all frequencies. It means when unit impulse will contribute equally to the all frequency from minus infinity to infinity. It's kind of a straight line, right, for all frequencies. Thank you for listening, and for Q&A session, we have an online separate session. Thank you very much.